Here we go with our second problem. And let's see if I can make this one go just a little bit faster. See if I can not have as many technology glitches. So right now we are looking at a particular problem with butterflies that are decreasing. And when scientists first started counting, there were 1,500 butterflies, and 1 year later there were half as many. This pattern seems to be continuing. Now there has been some worry about this related to butterflies. Those monarch butterflies that we'd love to see in the summertime. Haven't seen them as much in the last number of years, and I know there's some worry about that in the science community. Those monarch orange and black butterflies that you probably have seen. Okay, so time passed in years. We're going to do something similar to what we did on the last problem and figure out like time passed as our x value. So let's go with like 0, 1, 2, 3 years, and then let's go with the population of butterflies. And we start off with 1,500 of them, and then each year there's only half as many, okay? So that means the multiplier is 1/2, okay? So 1,500 times 1/2 would be half of 1,500, or 750. And then that times 1/2. Half of 750 is 375. Half of that, well, let's see, half of 375, let's see, 187 would be 374. So I think that's 187.5 then. I'm just going to start to do some mental math here. And I think we've got that right now. Okay, so exponential growth or decay, hopefully you are seeing this is a situation where we're looking at decay. Our numbers are decreasing. Our multiplier is between 0 and 1, which indicates decay. So our equation, or y-intercept value, or starting amount is 1,500 times 0.5 to the power of x. And then how many butterflies will there be after 6 years? And so that means that we can plug in 6 into our equation. So 1,500 times 0.5 to the power of 6. Well, please let me do this so that we don't have a lot of difficulty this time. All right, let's clear. 1,500 times 0.5 to the power of 6, and we get but 23 butterflies. 23.4 is what we have mathematically. I'd hate to see 0.4 of a butterfly though. So 23.4375, but really that means there's 23 whole complete butterflies. Okay, start at 1,500, and after 6 years with exponential decay, we're already down pretty close to 0, honestly. 23 butterflies is not a whole lot compared with that amount of 1,500. So if we're going to graph this, let's take a look at time passed again. And we're thinking about 0 years, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and butterfly population over here. And this time at least we know we have to start off with 1,500, so we need a scale that gets us up to 1,500. I don't know that 100s are going to do it. 1, 2, 3, 4, 5, 6, 7, 8, 9,000. So that's not quite going to do it. Let's go by maybe 150s, 200s even. So 150, 300, 450, 600, 750, 900, 1,050. We have 1,200, 1,350, and 1,500. So that actually works out really nicely. And so then graphing that, I'm going to switch colors again. We have 1,500 as our starting amount. After 1 year, we have 750. After 2 years, we have 375. So I've got to start approximating here. After 3 years, we have 187. All right, so we don't have the next one here, but you can see that if we plug in 4 in here, and maybe I will have to go back to the calculator just to get a couple more values here. So I go back to the calculator, and if I want to go ahead and basically just do the last problem here, but I want to go to the power of 4. That gets me 93.75. And if I want to do that again and do the power of 5, that gets me 46.75. So about 94 and about 47. So 94 and then 47. And we can see this is really getting very, very close to 0 here. So I'm not going to do any more, but essentially it's going to get closer and closer to 0. Theoretically, you can never quite reach 0, but certainly we can get below 1 butterfly under this pattern here. So eventually things do go extinct, right? So although the exponential decrease could never get quite to 0, certainly the actual practical situation here could get down to 0. So that is what we call exponential decay.